In this video, we're going to pick back up with the same study we ended our last video, looking at leptin values in various strains of mice and on various diets. We have already looked at the standard deviations and seen that they are fairly low compared with the average leptin concentrations, which means we can trust that the reported averages are consistent with what they measured for mice in a given sample. Now we turn to the conclusion they might make. Notice that the leptin values for the mice on the high-fat diet appear to be different, specifically higher than the mice on the control diet. So the question is this a real difference? Researchers get at this question by reporting what is called a p-value. This is how the p-value works. First, we assume that the two sets of data we want to compare are not actually different. That is, what if there is no real difference in leptin values between control and high-fat diet mice? We then use a statistical test to calculate what the odds would be of getting these numbers, again, if there were no real difference. A p less than 0.05 means that there is less than a 5% chance of that occurring if, again, there is no real difference. A p less than 0.01 means there is a less than 1% chance, again, assuming no real difference exists between these two sets of data. It is a fairly common practice to report p-values below 0.05 as statistically significant. But that can be misleading. A p-value less than 0.05 does not mean that there is only a 5% chance that the difference is due to random chance. Again, it assumes there is no difference and calculates what the probability is that we would still see these numbers. So how should you use the p-value? You should know that the lower the p-value is, the more likely any claimed difference is real. And you want to see a p-value less than 0.05, but less than 0.05 around 0.01 or 0.001 is even better. However, it's not enough just to consider the p-value alone. You also want to consider other information when evaluating differences between two groups, specifically something called effect size. Here's an example of effect size. Let's assume a different set of data for our hypothetical cholesterol drug experiment. Notice that the experimental group has lower LDL levels after 1 month compared to the control group. Assume we calculate a p-value of 0.05 and report this as statistically significant. So we are now claiming to have discovered a drug that produces a statistically significant decrease in cholesterol after 1 month use. There's just one problem. The lower cholesterol level reported for our experimental group is still a really high cholesterol level. This is effect size. The cholesterol levels are lower, but the overall effect is still quite small. So while the p-value can tell us about whether or not there is a real difference between two sets of data, effect size looks at whether or not that difference is truly meaningful. Now let's turn to some of the ways we can represent data graphically. Two types of graphs you will commonly see are bar graphs, which are useful for making comparisons about groups, and scatter plots, which are useful for a single group or sample with data collected over a period of time, or when you are trying to describe a mathematical relationship between your data. When looking at any graph, there are a couple of conventions to keep in mind. First, the horizontal axis is called the x-axis, while the vertical axis is called the y-axis. Data is always plotted on a graph such that the independent variable, remember this is the one that the researcher manipulates, goes on the x-axis, while the dependent variable, the measured value, goes on the y-axis. Let's look at an example of a bar graph and what to look for. This is a study measuring serum insulin levels in mice as a result of loss of the gene for the hormone glucagon. The mice without glucagon are designated GFP and are shown in black, while control mice are shown in white. What should you look for when examining this graph? First, let's make sure it is plotted correctly. The independent variable here is the pregnancy status of the mice as well as the mouse strain, as both of these are variables controlled by the researcher. The serum insulin is the dependent variable, as that is what the researchers measured. As far as the data itself, we can first check the error bars to give us a sense of the standard deviation. Notice how these are small compared to the reported averages, which is a good sign about the quality of their data. Also look for a p-value. This is often indicated on a graph by an asterisk, like the one we see here. This means that when comparing the two groups, pregnant control mice versus pregnant mutant mice, there was a difference based on a p-value of less than 0.05. Finally, you should check the axis labels themselves to make sure the scale they are using on their graph is appropriate. The y-axis of a graph doesn't always have to start at 0. This is from a paper looking at the blood pH changes that occur during and immediately after birth. Given that normal blood glucose should be within the very narrow range of 7.35 to 7.45, zooming in on the range of 7 to 7.6 on the y-axis makes sense here, so that the drop to 7.2, which is a large effect when talking about blood pH, is detectable. This ends video number 2. We will pick up in the next video talking about the second type of graphical representation, scatterplot.